So welcome back to the electrochemistry lecture. So far we have seen with the what do you mean by transport number and we will try to derive the relationship between transport number and its velocity or relationship between transport number and conductance. So now we will see the factors which will affect this transport number for one particular ion. So we know that the transport number basically tells you the relationship between what conductance and velocity for a specific ion. So these two factors are common. One is the conductance of a solution and another one is the velocity, and we know that velocity is also depending upon the various factors like size of the ion, concentration, likewise. So we'll see the factors one by one. So first is what? Mobility of the other ion with which it is being associated. So it is also a like velocity related factor, because velocity of cation will be also depending upon the density of solvent, also the counter ion, its counter ion. So that also decided the velocity. So first factor is the mobility of the other ion with which it is associated. Now the transport number of any anion which can be obtained by subtracting the transport number of cation, because we have already seen that the addition of transport number for the cation and anion is always unity. So if we have known the transport number for the chloride is suppose this much, then the for sodium it will be okay 0.604. So we just need to subtract the given value from 1, so we will get the transport number for the remaining ion. So for HCl, the chloride ion, there like here comparison of this chloride ion is taken place. So in first case we are considering sodium chloride. The sodium ion is having the transport number of 0.396, and chloride ion should have the transport number of what? Then 1 minus 0.396, which is comes out to be around 0.604. But if we consider the HCl molecule, so there the transport number for Cl is 0.166. So since the ions are same, like chloride ions are present in the both the cases, but the transport number is varying. Why is it so? So the reason is that the mobility of the hydrogen ion is much greater than that of the sodium ion. Thus it can be concluded that the transport number of an ion is does not depending upon the mobility of the that particular ion, but also it is depending upon what? The mobility of the other ion also with which it is being associated. So we can say that this transport number is depending upon the mobility of the itself. Means if we consider the suppose H plus ion, so its mobility will be depending upon velocity of that particular ion. But along with that, what will happen? Along with that, the mobility is also, or transport number is also depending upon the mobility of anion also, that which it is associated. So if we consider H plus, then we have to consider the mobility for the Cl minus also. So this is the one factor, that is the mobility of the other ion with which it is associated. Now the second factor is what? The hydration of ions. So we all know that this aqueous solution will resulted into what? Hydration of the given ions. So positive end will attract the negatively charged ions, and negative end of the water molecule will attract the positively charged ions. So the transport number of this three alkali ions, so for example we will consider lithium plus, sodium plus and potassium plus in their chloride, increases in the same order. Since the chloride ion which is being the common in the each case, so we can say that this increase in the ionic mobility is due to what? Increase in the speed of cation. uh, but actually the reason is that the lithium ion is smaller in size and it has high charge density, and therefore what will happen? Due to this, the higher hydration, large number of water molecule or water dipole is get attracted, and hence higher hydration will takes place in the case of lithium. And the potassium ion, which is having the largest sign among the three ion, which is like lithium, potassium and sodium, the alkali cation which has very low charge density, and therefore it will attract only a small number of water dipole. Hence the degree of hydration is maximum in what? Lithium, and it is minimum in the case of potassium plus. Hence the degree of hydration of the sodium plus is what? In between. And as a result we can say that this lithium ion is get highly solvated or highly hydrated in the solution state, and it is be in the, it will become what? Bigger in size than that of the hydrated Na plus, and later it will be the bigger in size in than that of what? Hydrated form of potassium plus. Hence we can say that the potassium plus ion in aqueous solution are moving faster, so it has the maximum speed or maximum velocity, and lithium ion is having minimum velocity. So the increase in the ionic mobility, or indirectly we can say that the conductance is not due to the size but is due to what? The hydration energy. So indirectly it is size, but it is the size of not ion, but it is the size of hydrations the sphere, or we can say that the solvated molecule. So that is also an important factor. Now next is the effect of concentration of the electrolyte. So concentration, we know that it will affect the overall number of ions present in the given solution. So if more number of ions are present, then there will be obviously more drag to that particular ion, so overall velocity is going to get decrease. So it is observed that this transport number will changes only slightly with increase in concentration of the electrolyte. However, it is found that the concentration which has marked effect only on the transport number of cadmium ion in the cadmium iodide, and the value is decreased from what? These are the experimental values. So value is decreased from 449 at low concentration, which is around what? 0.005 molar or 5 millimolar, to almost 0 uh, at higher concentration, which is zero point 0.5 molar. So why is it so? So this is due to the complex ion formation at higher concentration, which is represented as below. So cadmium iodide will dissociate at what? Cadmium 2 plus and 2I minus. But if we take the higher concentration of this cadmium iodide form the complex which is having the formula of cadmium tetraiodide, that is CdI4 2 minus. The sum of the cadmium which is formed part of this anion and get migrated towards anode. So overall the concentration of cadmium towards cathode is get decrease. Okay, because this cadmium which is formed in the complex is what? Is now anion, so it get attracted towards the anode. So overall cadmium concentration is decreases. So therefore we can say that the fall of concentration around the anode is as much as it should be, and if the anion is moving for faster than the cations, then there will be actually increase in the concentration around the anode, and we can say that this discharge process is imbalanced one, and overall we can have the decrease in the value of transport number, and hence we will get the lower value of conductance for the given solution at higher concentration. So this will explain the fall in the value of transport number for the cadmium ion at higher concentration. So here are the few numericals related with this uh, transport number, and so next factor is the ionic conductance and the transport number. So we have previously seen that the relationship between ionic conductance, that is lambda, and transport number relation. So we have already derived this, and we will try to see this in detail. So Collard's law of independent migration for the ion, which bring the fact that this ionic conductance at infinite dilution which has definite value at fixed temperature, and it is being independent of other ion with which it is being associated. So this is what? At infinite dilution. So this ionic conductivity at infinite dilution, however, depending upon the speed of ion in the solution. So we can say that this ionic conductance at infinite dilution for the cation is directly proportional to the ionic velocity of cation, and in order to remove this proportionality sign we have just taken the one proportionality constant, say k. Similarly, for the ionic conductance for anion is directly proportional to the velocity of anion. So again remove to that proportionality sign, we will again take the proportionality constant. Now we know that this molar conductance for the given solution is what? At infinite dilution, it is summation of ionic conductivity of the ions, that is for cation and for anion. So we just simply add up that two ions, that is lambda plus and lambda minus at infinite dilution is equals to what? K into v plus plus v minus, that is the velocity of cation and velocity of anion. Now according to Collard's law of independent migration of the ions for the infinite dilution, we can see this ionic conductivities for the cation plus ionic conductivity for the anion is equals to what? Molar conductivity for the given solution at infinite dilution. So therefore we can say this lambda naught is equals to k into v plus plus v minus. So upon dividing these two equations here, so just divide these two equations, equation number 2.27, this equation, any of this equation will do. Okay, so we'll take the first equation and this, now we derive this equation. So just deriving dividing that two equations, that is lambda plus upon lambda here, kappa should become is equals to k v plus upon k into v plus plus v minus. So this can get cancel out, so we have been again left with what? V plus upon v plus plus v minus, that is total velocity. So it is what we have already seen, this is equals to what? Transport number for the cation. So we can say that this transport number for the cation is conductivity of the that particular ion, that is the conductivity of cation upon molar conductivity, or we can say that the conductivity for the cation is transport number for the cation into molar conductivity. So these are the various forms related with the molar conductivity and the uh, transport numbers. Similarly, for the anion also we can obtain the same type of relation, that is uh, lambda minus at infinite upon kappa naught is equals to nu minus upon nu plus plus nu minus, which is what? T minus. So overall we can say this, the T minus is equals to lambda naught for anion divided by kappa naught. So these are the important equations relating what? The transport number and the ionic conductivity and molar conductivities. So for the electrolyte other than univalent, so in order to take the that coefficient which is present in the stoichiometric form, so for the um, unibivalent or unitrivalent or other than univalent ions, we just need to consider the stoichiometric coefficient. So this Q and R are nothing but the respective stoichiometric numbers for the cations and anions of the electrolyte. So likewise we have seen for the Collard's law for the other than univalent ions. So same type of equation can be obtained for the uh, unibivalent or unitrivalent as such ions. Now we have been left with one ionic mobility and ionic conductance point, and we will try to see some numerical based upon this transport number in the upcoming lectures. Okay.